Hi, this is Mrs. Cribb, and this is the lecture for 11C, Chapter 11C. So pull out your notes, please, and I'll need you to kind of fill in the notes where where it's needed. And I'll be referring back and forth between the notes and also the presing. So liquids, we've talked about liquids in the past, and we're just going to focus on them a little bit here. Liquids, particles that are held together by intermolecular forces, and remember those intermolecular forces. There are dispersion that all molecules have, and it's the only one for nonpolar, only for nonpolar. And there are dipole-dipole forces, and in order to have a dipole, which means two, that you have to have a polar molecule. So this has a positive side and a negative side on the molecule, so don't forget that. We'll have a, usually a positive kind of reddish end and a negative kind of colored in blue. And so there's intermolecular forces because another molecule would also have a positive and negative side, and the opposites will attract to each other. So that is the intermolecular force, the opposite charges attracting, pulling these molecules close together. And then the third type of intermolecular force we've talked about is a hydrogen bond. And a hydrogen bond is just basically a special dipole-dipole. It's an extra strong dipole-dipole. And you have to have hydrogen bonded to nitrogen, oxygen, or fluorine. And remember, those are the most electronegative elements. Fluorine's the most electronegative, and then oxygen is the second most, and then nitrogen is also very strong. And all they are is making a particular type of polar molecule that's just has a lot of strength. And I showed you some pictures about different ones that had hydrogen bonds. And then, so these are primarily for covalent, but if you have an ionic bond, don't forget that. That's going to be a pure positive and negative. So an ionic bond is the strongest one of the intermolecular forces. The attraction between these guys is much stronger because this dipole-dipole, this guy's right here, this dipole-dipole, it looks like a smiley face, doesn't it? This dipole-dipole, it is polar, but not nearly as strong over here. We're not pretty much permanently putting all the electrons in one spot or another. That's not really the exact right way to say it, but it's the, ionic, metal, non-metal, ionic, they transfer their electrons so that one molecule is positive and negative. So one part of the molecule, rather, is positive and negative. So in ionic, you might have sodium and chlorine. And so they build from that. So just to remember the strengths, ionic is strongest, and then we have hydrogen bonds is the next strongest, and then the dipole-dipole, which is polar, is next strongest, and then dispersion is the weakest. And in dispersion, remember that the bigger they are, the stronger they are. So the smaller they are, the smaller number of atoms involved in the molecule, the weaker it gets as well. And we'll review all of this together as well. So liquids, they have less energy than gases, okay? And we've talked about the kinetic molecular theory before. They have stronger intermolecular forces than gases. And what does that mean? They have less energy, they have stronger intermolecular forces. So the individual gas particles are flying around like crazy, going all over the place, just here and there and everywhere. And they have a lot of energy. But the attraction between these molecules is weak. And that's because the gas molecule itself has a lot of energy. These molecules right here have a lot of energy and they're flying around. Okay? So liquids have the individual liquid molecules don't have as much energy. So these guys are closer to each other than the gases. And because they're closer to each other, the intermolecular force between them, the attraction is stronger. Okay? The attraction between them is stronger. Liquids are not in a fixed position. They fill up any kind of particular position you want them to fill up. They can flow and be poured, so they're fluids. Liquids are fluids because they can flow. Gases are also fluids because they can flow. Fluids flow. Liquids are more dense than a gas, but less dense than solids. Remember, density is how close they are. So liquids are still pretty close to each other. Okay? And they kind of they roll around one another, but they're still pretty close. So it's really difficult compress a liquid because the molecules are already close together. Now, solids are very close to each other, so you can't compress them. But remember, gases are very far away, and they're easily compressible. Liquids can't significantly expand or compress. And that means they can expand and compress it just a tiny, tiny bit. But gases are very, very compressible. And if I talk about compressibility, I'm really going to be talking about gases. Okay? And this should have been a review. All right, now we're going to talk about cohesion and adhesion and different intermolecular forces there. Co means together. And if you're adhering or cohering to something, you're sticking to it. So co is attraction between the particles of the liquid. They're sticking to each other. Co is together, so sticking to each other, coming together, like cooperating or coming together. Cohesion, cohering, adhering. We're sticking together. And then surface tension is the elastic skin that forms on the liquid. It's produced by an imbalance of intermolecular forces. I'm going to show you some pictures in a minute. The ones at the top of the liquid are being attracted down. So like if we have a liquid and we have a bunch of molecules in this liquid, okay, and they're all in this liquid floating around, they're all fairly close together, and they have intermolecular forces attracting them to each other. But on this top layer, right up here, see how they are attracted across the top and down, but they're not attracted up. So the other guys are also attracted up. The ones in the middle are attracted up. These guys here, they have attractions that are attracting them to molecules above them. All of these do. But the ones at the very top, they only are attracted sideways and down. So that causes surface tension. Now a surfactant is a surface active agent. Surfactant, surface acting. And they break down surface tension of water by interfering with the hydrogen bonds, and so they allow things to kind of sink through them. So if you can mess with the surface tension at the top, if you can break it apart, if I can do something to cause this down here to kind of break apart, then any object that's floating on top of it, like maybe a paper clip, will sink through it. Okay? So a surfactant breaks apart this surface acting agent. It breaks apart the surface tension. That's what a surfactant does, is a surface acting agent that breaks that apart. And it allows things to go through. It allows grease and oil and other non-polar liquids to dissolve. Viscosity, the ability to resist flow, basically how thick it is. The more viscous, the slower it flows. At cold temperatures, particles are have less kinetic energy, less movement energy, so they flow more slowly. Think about syrup. Cold syrup is very viscous. So if it's cold, it's more likely to be viscous, okay? Because it has less energy, less thermal energy, less kinetic energy, okay? Warm syrup flows quickly because it has less viscosity. Cold syrup has more viscosity. That's the ability to flow. So it's viscous. If it's viscous, it's thick. I somehow think of it that way. If it's viscous, it's thick and it flows slowly. And it's usually cold. Then we have adhesion. And adhesion, think about an adhesive band-aid, okay? Ad means like to move towards something. So adhesion is to stick towards something else. So particles of the liquid and the particles of something else, adhesion. Cohesion is sticking together. Adhesion, sticking to something else. And the meniscus is the result of the intermolecular forces between the liquid and a container. So a meniscus is this thing right up here. This is the meniscus where the liquid and the container are interacting, and it causes it either to go up or down. I'm going to show you some pictures in a minute. When the attraction between the container and the molecules exceed the attractions between the liquid molecules. So when the attractions between the container and the molecules, adhesion, exceed the attraction between the liquid molecules, cohesion, the liquid climbs up the walls. So here, That's what's happening here. Adhesion is greater than cohesion. The attraction between the liquid and the container is stronger than between just the liquid itself. So in adhesion, the particles pull up because that attraction is stronger. In cohesion, here, the attraction to themselves is stronger than attraction to the container. And then in a capillary tube, this is exaggerated, and I have some that I'll show you in a minute. So let's look here. This is showing you some cohesion and adhesion. So here, it's adhesion down here because it's a liquid sticking to a surface of something. That's adhesion, okay? Up here, it's cohesion because the liquids are sticking to each other. Okay, the liquid is sticking to the liquid. All right, now I'm going to go over to the Prezi for a moment. Okay, I have here a picture just showing you how a liquid takes the shape of any container that it's in. And notice how it just fills whatever and goes up to the same level. And then this is showing you the densities of a solid very close together, of a liquid. Notice they're still close together, and a gas very far apart. Gases are very compressible. Liquids are only slightly compressible. And same thing with solids. All right, and then we went through all of this, and this is just showing you some different surfactants, surface acting agents, things that break up that surface tension so that other things can go through it, okay, through the top. I'm going to skip that one. I'm going to watch this for a minute. Take it a minute. Here it comes.
Hey, welcome to NASA Launchpad. I'm your host, Audrey Staples. You might have heard the saying that opposites attract. And you know, that's true in a lot of cases, like in some bad romantic comedy. Or when you bring a pair of magnets close to each other. North and south poles will snap together. But sometimes, like with water, molecules of the same substance attract. Wonder why? You'll get a better picture of why when you get the chance to see water someplace other than Earth. Like on the International Space Station, commonly referred to as the ISS, where water appears to be nearly weightless. Here's Canadian Space Agency astronaut Bob Thirsk on the ISS with a closer look at water and this special property.
The intermolecular forces cause water to be attracted to itself, which is called cohesion. For example, here are two spheres of water. When the spheres are several centimeters apart, there's no attractive forces between them. But when I bring them close enough together to attract, they merge through their attractive forces.
So, you probably already know that water molecules are attracted to other water molecules, and that's called cohesion. Well, these same cohesive forces are responsible for surface tension. Surface tension is the property of a liquid that makes it beat up when it drifts on the surface, like a leaf or your skin or a coin. Water surface tension is pretty strong. You can check it out with an eyedropper of water and a penny. Take a closer look. See what happens when you squeeze the water out onto the penny, one drop at a time. How many drops do you think you can gently squeeze onto the penny before the water spills over the side of the penny? I bet it'll be more than you expected. Surface tension is what allows the water drops to cling together, forming that dome or bulge at the top. You can see that water surface tension is pretty strong. You can also see the cohesion of the water as it stuck to itself. But the water did something else as well. It stuck to the penny too. Why was that? Here's Bob again to explain and to show how it works in space.
Intermolecular forces can also cause water to be attracted to other materials. This is called adhesion. For example, water can stick to a straw. When I move the straw close to the sphere, The water sticks. Water sticks to many other materials as well. Think about all the things on Earth that you see little water drops on. Windows, tree leaves, even your own skin. Let me show you with my hand. The molecules in my skin will pull hard enough to make the water stick. The water tries to find a balance between the cohesion with the water and the adhesion to my hand. Eventually it settles on an unusual shape that fills the space between my fingers. If I continue by adding water, I can eventually build an entire glove of water that will stay fixed to my hand. It sticks to my hand by intermolecular forces. How cool is that?
All right, so that brings us to just again showing the surface tension, the unbalanced forces. These are all attracted down and across, but not up, and these are attracted in all directions. And these are showing you cohesion causes the drops to form, and adhesion causes the drops to stick to the plant. And remember, there's a surface tension around the outer edge. So cohesion, adhesion, and surface tension are at work on all of these. There's another example of cohesion and adhesion. This is xylem and phloem, so inside the plant. And the xylem is right here, and the water is sticking to the side, but it's sticking to itself. And that helps it to kind of go up into the plant, into a vascular plant. And I'm trying to find the pictures. There's again adhesion, the particles are sticking to the container, and cohesion, the particles are sticking to themselves. So this is when adhesion is stronger than cohesion, so it kind of crawls up the edge. And this is just another little thing. Cohesion sticking together, adhesion sticking to something else. All right, and that brings us to a couple of meniscus right here. This one is where adhesion is stronger, going upwards, and cohesion is stronger here. They're sticking to themselves more readily than they are sticking to the side of the tube here. So hopefully you can get adhesion and cohesion down pretty well. And that brings us to vaporization in your notes. Vaporization, molecules above average speeds that break away from the liquid phase. So vaporization happens at any temperature, and it happens from the top, okay? It can occur at any temperature because the liquid molecules are moving at different speeds and hit and transfer energy, kind of push them out of the way. Condensation is the reverse of vaporization. You form a liquid from the gas. So that means that the gas is moving fast and so loses some energy. Maybe it hits a cold pocket of air, loses some energy, and so the particles get closer together and reform a liquid. Vapor evaporation is vaporization below the boiling point. It's a cooling process. When you have water on your skin and it evaporates, it removes heat from your skin because the heat from your skin is being used to break those particles apart. And then vapor pressure is the pressure exerted by the vapor molecules over a liquid. So hold on, let me go back to this for a minute and see if we can look at this vapor pressure picture here. We have vapor on top and a liquid on the bottom. The vapor is escaping, but it's also pushing down on this liquid right here. And then we have just some more pictures. This shows you condensation on the outside of the cup, and that's because when the air gets close to the gas, right around these edges of the air is colder than it is out here, and so the water molecules slow down, and their attractive forces make them come back together. So they no longer have enough energy to fly away from each other, and so they reform. That's when condensation happens. So the upward arrows here are showing you how it evaporates, how the water molecules or the liquid molecule will evaporate. But when it evaporates, they are flying around in this closed container, and they're pushing down on the liquid. And so there's going to be something called vapor pressure, the pressure of the vapor. And that was that one as well. That brings you to boiling. Now I'm kind of going through this fast because we will also talk about it in class, and there's a Quizlet that you can use and a Kahoot that you can use, and also because a lot of these terms are familiar. Boiling is vaporization that occurs at the boiling point. The boiling point is when the vapor pressure of a liquid equals the atmospheric pressure. The vapor pressure equals the atmospheric pressure. So the atmospheric pressure is all the air above you pushing down. When the vapor going up out of the liquid equals the pressure pushing down, that's when you're going to have something boil. Okay? When the air above equals the vapor above, the evaporation, there's evaporation, and then here's boiling. When the vapor pressure pushing up equals the atmospheric pressure pushing down, you're going to get boiling, okay? Vapor pressure equals atmospheric pressure when it boils. Evaporation, the vapor pressure is less than the atmospheric pressure. Evaporation happens only at the top. Boiling happens all the way through. There's a couple of more pictures about that we'll go through. Temperature and pressure affect boiling point. The lower the atmospheric pressure, the easier it is to boil. Now, it is easier to boil water on top of a mountain than at sea level because, well, think about it. And to boil, the atmospheric pressure has to equal the vapor pressure. The pressure of the atmosphere pushing down on you has to equal the pressure of the gas escaping, the vapor coming up out of the liquid pushing up. Well, the higher you are on a mountain, the less air pushing down on you. So it's easier to boil something. It's easier for the vapor going up to push that air away. The normal boiling point, though, is the temperature that you call boiling when you have a pressure of 760 torr, or 1 atmosphere. And as temperature increases, liquids change to gases faster, and thus their vapor pressure will increase. So as temperature increases, liquids change to gases faster because they have more kinetic energy, and thus vapor pressure, that's the pressure of the gas escaping, increases. Okay? Here, there's a show you again. There's the atmosphere, a lot of atmosphere pushing down on this little red ball. But if you're on top of a mountain, less atmosphere pushing on this little red ball. So it's easier to boil things up here because it's easier to push that little bit up than it is to push this little bit up. Okay? This is to show you how that affects it. On a lot of recipes, they change the instructions depending on where you are. So at high altitudes, they tell you they cook this cake in a different way. And that's because it boils and it affects the way it cooks differently. Okay, so let's look at some things. Now we're going to look at some charts on boiling point, and these are super, super easy to use. So I forgot what the question was here. What is the boiling point of water that is subjected to an atmospheric pressure of 500 torr? So we're going to look at the picture. What we do is we look at these three things. Water is this line right here. And then this one is ethyl alcohol, and this one is diethyl ether. There's the temperature in degrees Celsius across the bottom, and the vapor pressure in torr. Torr is just a unit that we use to measure pressure. So the question said, what's the boiling point? I actually forgot the question. I'm going to have to go back and look. What is the boiling point of water that's at 500 torr? That's probably why I drew that line. Okay, so here's 400 torr and 600 torr. So right in the middle would be 500. So you go across the torr until you hit the water line, and this is the curve for water, and then you just go down and read the temperature. So this is 80, so that's 90, so it's about, maybe 87 degrees Celsius. So what would the boiling point of water be at 400 torr? Well, I go over here, I find 400, I go across the chart until I hit water, I go down and read it, and it's somewhere like 82. So what's the boiling point of diethyl ether at 500 torr? There's the diethyl ether line. So there's 500, you go across, you hit diethyl ether, go down and read it. It's around 22 degrees Celsius. And then what's the normal boiling point? Well, that's at 760 torr, or 1 atmosphere of pressure. So the normal boiling point for diethyl ether would be 34.6 degrees. The normal, and go straight across. The normal boiling point for ethanol is 78.3 degrees. See, we go down and read it. And the normal boiling point for water is 100 degrees Celsius. So the normal boiling point, the one referred to for standard, is always always at 760 torr, or 1 atmosphere, because pressure affects the boiling point. So we have to kind of designate which one we're going to call a standard. Okay, now, so this is another chart, and it shows vapor pressure and temperature and normal boiling points. And it gives you lots of different things. Here we have just plain old bromine, this light green color. And there's the normal boiling point for bromine at 760 torr, or 1 atmosphere. All right, I'd go down and read it, and it's a little above 50, like 53, 52 for bromine. And then, let's see, this is what diethyl ether looks like. Mercury, the metal mercury. Okay, that's this one right here. So its normal boiling point is above 350 degrees Celsius. See, at 760 torr, go across, find the curve for mercury, and go down and read it. Okay, so I hope you understand how to read these. I will review those with you in class as well. And these are the ones that you have in your notes. The next thing we have is a phase diagram, and this is something you need to be able to read as well. Also very easy to read. So what we have is in this area right here, all that area, that's where you would have a solid. So that solid would be at negative 79 degrees up to about 0.01 degrees Celsius. And this shows you the pressure and the temperature. So what you do is a cross section, okay? So at negative 10 degrees Celsius and somewhere in here, torr, I would just go up and intersect it and say, oh, it's a solid. The normal melting point is right there. That's the 760 torr, and then the 0 degrees Celsius. Okay? Normal boiling point would be 100 degrees Celsius. So this is a phase diagram for water. In this whole section, if I go up from that temperature and go across, in this whole section, I would have a liquid. Okay? So this even though this is a good diagram, it doesn't have good markings on it. I think I have one that has better markings on the next page. But you are going to need to know things like the triple point, and that's where all three of them can exist at once. Solid, liquid, and gas. See, there's solid, a liquid, and a vapor can all come to that point. And the critical point, which is this one way up here, and that critical temperature is where no matter how hot it gets at that point, I could never, or how much pressure I apply, it's too hot and the pressure would have to be too strong, I could never turn it into a liquid. If it goes above this point, this way or that way, I can never turn it into a liquid. It's called the critical temperature. We have another picture down here with the same kind of deal, and it also shows you that deposition, going from a from a gas to a solid, see, vapor to solid, straight across that line, vapor to solid is deposition. Going straight from a solid to a vapor is sublimation. There's the triple point here. Going from a liquid to a solid is freezing. Going from a solid to a liquid is melting. Going from gas to a liquid is condensation. Going from a liquid to a gas is vaporization. Okay? And that brings us to distillation. The process of separating liquids into fractions using the fact that each part has a separate boiling point. There's a picture in here. You're not going to have to look at this figure. A phase diagram, that's what we've been looking at, has the triple point. It can exist at all three phases and the critical temperature, the highest at which a gas can be liquefied. Beyond that, we cannot push the molecule together anymore. Remember, if we push molecules together, we can change them from a gas to a liquid. So if it gets too hot, has too much energy, we can't change them from a gas to liquid anymore. So here's an apparatus they use for distillation. So we put some liquid in here, and maybe 2 liquids, and we heat it up to the boiling point, and it flows through here, and it gets cooled back down to a liquid, and it drips out. And the temperature of this liquid will not change until all of that first, whatever we're trying to separate out of it, comes out. And then it will heat up some more. So I'll talk a little bit more about distillation, but it's not all that important for you. It's another, I like this picture a little bit better because it shows you the separation. So inside this mixture we would have methanol and something else. And we heat it up until the methanol becomes a gas. Methanol and toluene, that's what TOL is. So methanol and toluene are in this liquid. and we heat this liquid up until it reaches the boiling point of methanol, which is 64.7 degrees. When that happens, methanol turns into this gas, and it floats up and floats to here, and we send cold water around it to cool it back off, and it drips out and comes into this round bottom flask. And so inside here we'd have methanol, but the toluene is still over here because toluene's boiling point is 110 degrees. So distillation is a way of separating liquids using the fact that they have different boiling points. Okay? All right. So let's move on. We did all that. So I like this one better because it has better markings for you to see. The scale is a little bit easier to see. So here we go. So let's just practice for a minute. There's the triple point where you can have a solid, you can have a liquid, and you can have a gas. And so what would I have if I had something at negative 20 degrees and 40 atmospheres of pressure? There's the atmospheres of pressure. So I go up to 20, and I go over from 40, and I'm sitting right here, and that's where it's a liquid. So this is the phase diagram for carbon dioxide. All right, what phase would I have if I have something at 0 degrees Celsius and 20 atmospheres of pressure? So go up, there's 0, go over, it's sitting right here in that spot. It's a gas. So at that point it's a gas. What about 0 degrees Celsius and 100 atmospheres of pressure? So it has more pressure. It's pushing the molecules together. Well, even at 0 degrees Celsius, with 100 atmospheres of pressure, I now get a liquid. Okay? What about at negative 80 degrees? Even at 140 atmospheres of pressure, it's still a solid. Even at negative 80 degrees, I should say. It's not nearly hot enough. So it just shows you, you just go up there and intersect. Do I have a solid, a liquid, or a gas? And the critical point, or the critical temperature for carbon dioxide is this right here. So 30.98 degrees Celsius. Any higher than that, it's very, very difficult. It's almost impossible to cause it to change from a gas to a liquid. And this is another one with more of the same kind of thing on it. And I will probably ask a few questions about this for you in class. Just go through it. Okay, now this is the homework page that we've already done. This is page 13. And so this is page 14 with the phase diagram in it. Okay? So I will go over this page 14 with you in class, and we'll make sure that we can understand all these different things. And don't forget to go back to the Quizlet. So that's really the end of our notes. Go back to the Quizlet to study your terms. You can play the Kahoot. And there's some review videos on dispersion forces, vapor pressure and boiling, more about hydrogen bonds that you might be able to benefit from getting ready for the test. Okay, I don't want to listen to it right now, so I need to stop this. All right, minimize this. All right, this is the pictures from your notes. This is the end of your notes. So again, I'll ask more questions about these intersections in class, and I will see you soon.